Hello and welcome back to our first lecture on limits. You might say this is our first real calculus lecture because the last two times we reviewed pre-calculus, looking at some of the skills we'll need to be successful in this calculus course. So now we're going to turn to limits for the next three lectures. You might remember that back in lecture 1 we briefly saw a limit when we were solving the tangent line problem. But today we'll have a closer look at the concept of limit, looking at some examples of functions that have limits and others that don't have limits. And also we'll approach limits from three different viewpoints: the so-called graphical approach, numerical approach, and then an analytic approach. But before I get deeper into limits, let's quickly review the tangent line problem that I looked at in lecture 1. You might remember that this is one of my favorite problems, and it was to find the equation of the tangent line to the parabola y equals x squared at the point 2, 4. Remember how we did this. We took a nearby point called Q with coordinates x, x squared. We formed the slope equation joining P and Q for that line segment. And that equation was x squared minus 4 over x minus 2. We then simplified by factoring the numerator and discovered that the slope was given by x plus 2. And then we said, let's take a limit as x gets closer and closer to 2, and that slope turned out to be 4. That sort of gave us a very informal look at limit. Let me now look at a definition of limit. This definition has some flaws, as you might see in a moment, but this is sort of an informal way of understanding what a limit is. Here's what we say. If a function f of x becomes arbitrarily close to a single number L as x approaches c from either side, then we say that the limit of f of x as x approaches c is L. And we write it as follows: limit, and then underneath x approaches c, of the function f of x equals L. In that previous example, we would write it as the following: limit as x approaches 2 of the function x squared minus 4 divided by x minus 2, and then we simplified that to be the limit as x approaches 2 of the function x plus 2, and then of course you can just plug in the 2 now, and you get the answer 2 plus 2, or 4. Now, as I said, that definition has a few flaws because words like arbitrarily close, from either side, approaches, those are not well defined. I'll talk about that a little bit later. But for our usage, it's a perfectly good definition. Again, in that previous example, remember what we did. We factored the numerator, canceled the common factor of x minus 2, and discovered that the quotient equals x plus 2 as long as x is different from 2. Now I want to take a closer look at this. Here we have two functions. One of them is the original x squared minus 4 over x minus 2, and the other is x plus 2. Well, that second function is a straight line, isn't it? It's the line x plus 2. The first function is the same as the second function, except it has a hole in it at x equals 2. I like to call it a line with a hole in it. So these two functions, the original one and the simplified version, agree everywhere except at x equals 2. And they have the same limit as I approach the hole, as I approach 2. Because it's never important in limits what happens at the point you approach. Let me repeat that. When you're taking a limit as x approaches c, it doesn't matter what happens at c, but rather what happens arbitrarily close to c. Let's keep that in mind as we proceed. I'd like to look now at a more interesting, a little bit bigger example, a little more complicated. Let's find the limit of the function x divided by square root of x plus 1 minus 1 as x approaches 0. Now, of course, you might think, let me try just plugging in 0. See what happens. Well, the numerator would be 0, and the denominator would be 0 plus 1 is 1, minus 1 is 0, and you get an expression 0 over 0, which is indeterminate. You can't tell what it is. So plugging in the point you're approaching will not work here. We're going to have to do a deeper study now. You can't just plug in the point. And what I'm going to do is a three-pronged attack. I'm going to look at a picture, a graphical approach. Then I'm going to do a numerical approach, plugging in some numbers near 0. And then I'll do an analytic approach using some algebra. So here's a picture of the function whose limit we desire. We want to know what happens to this function as I get closer and closer to 0. Well, look what's happening. Again, it's not defined at 0, but it looks like it's getting very close to 2 as I approach 0. So graphically, my guess is that the limit's going to be 2. Let's now look at a numerical approach. Take your function, x divided by square root x plus 1 minus 1, and plug in a lot of values near 0. In this chart, you'll see that I've plugged in values like 0.01, 0.001, etc., and then some points on the other side of 0, like minus 0.01, minus 0.001, etc. I've plugged in values getting closer and closer to 0 from both sides of 0. Well, look at the output of this function. We get values like 1.99499 when I plug in minus 0.01. And from the table, I think you see that as I get closer and closer to 0, the function values are getting closer and closer to 2. So we've done it graphically, and we seem to think the answer's 2. Numerically, it seems to be 2. Let's now do it algebraically. Let's take our original problem and manipulate it in such a way that we can figure out the limit without a calculator. So here's our original expression, and what I'm going to do is multiply by the conjugate, meaning I multiply numerator and denominator by the square root of x plus 1 over square root of x plus 1 plus 1. And that's really multiplying by 1. I'm not changing the expression. When I do that multiplication, look what happens. The denominator is the difference of two squares and simplifies to x plus 1 minus 1. And then I can cancel the 1 and the minus 1 in the denominator, and I'm just left with x, which will cancel with the x in the numerator. So after all that algebra, and I admit there's a lot of algebra here, you can see how pre-calculus plays a big role in calculus, we come down to the simplified version of our original function, and it's now square root of x plus 1 plus 1. Now, that limit as x approaches 0 of that final expression is the same as the limit of the original expression. And of course, in that final expression, it's very easy just to plug in 0, and you get 1 plus 1 equals 2. So the algebraic technique also shows that the answer is 2. Now, let's talk about this a minute. We approach this 3 different ways. I think you might agree that the graphical and numerical solutions are not really proofs. It's kind of looking at what a computer is telling us or a calculator. I like to say that these serve to verify the solution. Mathematically speaking, it's that algebraic approach that really is the correct one. I kind of remember when I was a student that we didn't have graphing calculators. It's a long time ago. We used slide rules, or our brains, to do multiplications and to draw pictures and things in mathematics. It was a tough time, and we only used the algebraic technique for finding limits. We had no visualization of what was really happening. I think things are a lot better now that we have graphing calculators and computers that can help us verify our algebraic work. Now, here's a problem I like to do in class. I talk about limits for a while, and then I ask the students a question, and it's really to test me if I've explained things correctly or not, if students are understanding me. Let's look at the following problem. Here's a function defined by two rules. The first part of the rule is that the function is 1 when x is not equal to 2, and then it's equal to 3 when x equals 2. Here's a graph of that function. It wants to be 1 everywhere, except at 2, it jumps up to 3. I like to call this a hiccup function because it goes along, it has a hiccup and jumps up to 3, and then goes back down to 1. And the question is, what's the limit of this function as x approaches 2? Well, the point of this is that the limit is 1. As x approaches 2, the function equals 1. It's irrelevant what happens to this function as x equals 2. If x equals 2, the function is 3, but that's irrelevant. What counts is what happens as x gets closer and closer to 2, and as x gets closer and closer to 2, the function is always equal to 1. So that's the answer. Let's briefly now look at some examples of functions where limits fail to exist. These are kind of interesting functions that give us a view of understanding limits by showing cases where the limit fails to exist. As a first example, let's look at the function absolute value of x over x. In a minute, I'll show you the picture, but let's see what it's going to look like. When x is positive, the absolute value of x equals x, and that's just x over x, or 1. So for positive x, the function value is 1. But how about if x is negative? Well, if x is negative, then the absolute value of x is minus x, and so that function is minus 1. So for x positive, the function is 1. For x negative, the function is minus 1. These don't agree, do they, as I approach 0? And so, as you can see from the picture, the limit doesn't exist to 0 because as I approach 0, the function is not settling down at a single value L, but rather it wants to be 1 from the right and minus 1 from the left. By the way, we call those one-sided limits. But for our case now, the limit does not exist because the function does not approach a single value as x approaches 0. I like to call this function the diving board function because you're kind of motoring along at the position 1 and then you jump off down to minus 1. Here's another interesting function for which the limit doesn't exist as x approaches 0. It's the function 1 over x squared. Now, let's see how this behaves. Let me approach 0 from either side. What happens to x squared? Well, x squared will be very, very small, won't it? A small number squared is small. And then 1 over a small number is very, very large. Like if you plug in a tenth squared is 100th, and a 1 over 100th is 100. That's getting pretty big. So as I approach 0 from either side, this function seems to be getting larger and larger. Here's a graph of that function. And you can see that as I approach 0 from either side, the function is going off to plus infinity. We say that this limit does not exist because it's not approaching a fixed number L. Later on, we will say that the limit's infinity. But for the time being, just say this limit does not exist because it's not approaching a finite number L. Good. Now I'm going to look at a little bit tougher example, but I think it's a more interesting example. This is one of the most fascinating examples, I think, to show on a graphing utility. It's the function sine 1 over x as x, and we're going to look at the limit as x approaches 0. So what does sine 1 over x look like? Well, let me first show you a picture of it. And this is a difficult picture to show on your graphing utility, because here's what's happening. As I get closer and closer to 0, this function goes up and down between minus 1 and 1 infinitely often. It just goes crazy as it's getting near the origin. Just up and down, up and down, up and down. I invite you to graph this on your graphing utility, and then zoom in near the origin, you'll see this chaotic behavior as the function goes up and down, seeming to, that kind of tells us, I think, that, hey, this limit is not going to exist. This is not a well-behaved function. It's doing crazy things near the origin. Let me convince you of that algebraically. This is a little complicated, but bear with me. I'm going to look at the function sine of 1 over x, and I'm going to take some numbers near 0, because I'm interested in what happens near 0. For example, let's plug in 2 over pi. Well, what's sine of 1 over 2 over pi? That would be sine of pi over 2, which is 1. Then plug in sine of 2 over 5 pi. And when you plug that in, you get sine of 5 pi over 2, which is also 1. And then plug in 2 over 9 pi. That also equals 1. I think you see the picture, don't you? This sequence of x values that I plug in all give 1 when I plug them into the function. But here's another sequence of points that gives -1. Plug in 2 over 3 pi. That would be sine of 3 pi over 2, which is -1. Then plug in 2 over 7 pi, 2 over 11 pi, etc., and you get a sequence of values going to -1. That's why it keeps going up and down between 1 and -1, and all values in between. It's a crazy function, but it's kind of interesting, I think. There it is. And by the way, we'll come back to this function next lecture and look at it a little closer. Well, what about this limit definition? What about this concept? Let me be the first to say that it's difficult. And historically, the concept of limit was difficult for mathematicians and scientists to figure out. It wasn't until the 1800s, well after calculus had been developed by Leibniz and Newton, that the formal definition of limit was given by Bolzano and Cauchy. Until then, mathematicians kind of had a feel for limits, but they didn't fully know how to write down a precise definition. Remember those words I used earlier, like getting close to and as close as you want and approximately? It's tough to make that precise. But if you look in any calculus book, you'll see a precise definition of limit. It's very complicated. It's called the epsilon delta definition. And I remember as a student, we had to work with that definition. I never understood it. I didn't know what I was doing. It was a manipulation of symbols, just blindly doing stuff. We like to call it sort of a way to torture our students. And it never led to any deeper understanding of what limits do, what they're for, or how to calculate them. So I invite you to go look at the definition of limit in a calculus book. We'll have it in our workbook, of course, but we will not need that formal, difficult definition to be successful in this course. That said, limits have very nice properties that can be proved using that definition, but I think you'll believe most of these properties just informally. For example, the limit of a constant as you approach any point is, of course, equal to that constant. The limit of the function x is, as you approach c, is just c. And in fact, if you have any polynomial like x to the n, the limit as x approaches c would just be c to the n. We like to say in mathematics that nice functions have nice limits. Things are well behaved for nice functions. Then we have properties of how to manipulate two different limits. You might have the function f with limit L and the function g with limit k, both as x approaches c. You can add them, subtract them, and you add and subtract the corresponding limits. A constant times a limit can be written, you pull the constant outside the limit sign. The limit of a product is the product of the limits, and the limit of the quotient of two functions is the quotient of the limits, of course assuming that you aren't dividing by 0. Good. Let's do now a little more interesting example to see how to calculate some limits, and then I'll give you a strategy in general on how to calculate limits. Let's look at the function x cubed minus 1 over x minus 1 as x approaches 1. Now, naively, I'd say plug in 1, see what happens. Well, if you do that, the numerator and denominator both vanish, and it's meaningless. Remember, you can't divide by 0 in mathematics, so it's not at all obvious what this answer is. Well, let's do some manipulations. The numerator can be factored using a pre-calculus skill, right? And so x cubed minus 1 factors to x minus 1 times the quantity x squared plus x plus 1. By the way, I suggest that you memorize the formula for the difference of two cubes and the sum of two cubes and how to factor it, because these seem to occur a lot in calculus problems. And now we have a common factor of x minus 1 in the numerator and denominator, so let's cancel that common factor, and we're left with a new limit problem. What's the limit as x approaches 1 of x squared plus x plus 1? Well, duh, just plug in 1, and you get 1 plus 1 plus 1 equals 3. Now, a couple of points here. One is we needed a lot of pre-calculus to be successful with this algebraic manipulation. And more to the point here, we started with an expression x cubed minus 1 over x minus 1, and we manipulated that to get an expression x squared plus x plus 1. Those two functions agree everywhere except at one point, and that point was x equals 1. The point we're approaching. But in terms of limits, that's irrelevant. Because remember, you don't care what happens at 1. You want to know what happens nearby. And nearby, these two functions agree, and the second function tends to 3. So what's a good strategy for finding limits? Suppose I give you a limit problem. Here's one, blah, 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 blah. What will you do to attack that problem? Well, you always should try plugging in the number, just direct substitution. Sometimes that'll work on simple problem. For example, if I asked you, what's the limit of cosine x as x approaches pi? Well, you'd go, hey, cosine pi, that's minus 1. That's the answer. No problem. I'm not dividing by 0. I'm not taking square roots of negative numbers. Things are well behaved here. So that limit's very easy to figure out. Now, but in most problems, you'll find you can't just plug in the number, like the previous example. You notice that it took some algebraic manipulation. So the trick now is, if you have a problem where you can't just plug in the number, do some algebraic tricks, some kind of massaging of that problem to get another function that agrees with the original function, except at one point, the point you're approaching. And then those two will have the same limit. And then when you're finished, what do? You got this answer. Well, you should verify it. You should make sure you're correct by either using a table of values or a graph. For instance, in that previous problem, we could have graphed the original function, x cubed minus 1 over x minus 1. And I invite you to do that when you go over your lecture notes today. And if you do graph it, you'll see that indeed the function wants to be 3 when x gets closer and closer to 1. Now, there's a very important limit that occurs in all through calculus that deals with the function sine x divided by x. And the question we're going to look at right now is, what's the limit as x approaches 0 of sine x over x? It's really an interesting problem. You could approach it, of course, the 3 different ways. You could look at the graph of this function, and I'll show you in a minute the graph, and see what the function is trying to do near 0. Or you could look at a table of values. Of course, you can't just plug in 0, can you? If you plug in 0, you get 0 over 0, which is not defined. So we're going to have to do something. Or you could do an analytic approach, and it's a fairly complicated analytic approach. It's in most textbooks, but it requires some geometry and something called the squeeze theorem, and I don't think we'll go into those details right now. But if you look in a calculus text, you'll see an analytic approach to this limit. But let me show you the graph of the function. Here it is. And it looks like that as I get closer and closer to 0, the function seems to be getting closer and closer to 1. And as x gets further from 0, you can see that the sinusoidal behavior, the wave behavior, begins to dampen. The waves get smaller and smaller as I get further away from the origin. But what we really care about is what's happening near the origin. And near the origin, when x is near 0, the function is getting closer and closer to 1. Another way of saying that is, when x is small, sine x and x are approximately equal because their limit is 1. Isn't that interesting? You might remember that from physics, because sometimes when you're doing pendulum problems, they say, assume that sine x and x are approximately the same. So, we have this limit, sine x over x, as x approaches 0, and that's equal to 1. A related limit that comes up a lot is the limit as x approaches 0 of 1 minus cosine x over x. That limit turns out to be 0, and it's instructive to see the analytic proof of that. So let me step through that limit as x approaches 0 of 1 minus cosine x over x. I think you'll like this little proof. It uses some neat techniques. So what I do is I multiply numerator and denominator by 1 plus cosine x over 1 plus cosine x. That's very much like rationalizing the denominator. So look what happens. The numerator becomes 1 minus cosine x squared. And oh yeah, I remember my trig identity. Remember? Sine squared plus cosine squared is 1. That means that 1 minus cosine squared is sine squared. So I replace the numerator with sine squared x, and my denominator is still x times the quantity 1 plus cosine x. And now I do some sort of moving people around. I take one of the sine x's and put it on top of the x. So I have sine x over x, and then I take everybody else, the other sine x, and put it over 1 plus cosine x. So now I have a limit of a product of two functions. The first function is sine x over x. What happens to that function? What's its limit? That limit is 1. We just talked about it. What about the limit of sine x over 1 plus cosine x? Well, let's plug in 0 and see what happens. The numerator is 0. What's the denominator? It's not 0, is it? It's 2. It's 1 plus cosine 0. Cosine 0 is 1, so it's 0 over 2. So this limit is 1 times 0, or 0. Okay, that was a pretty complicated algebraic solution, wasn't it? How would you verify that? How would you make sure you did it correctly? What would you do? Right. You could draw a picture of the function. You could have your graphing utility graph 1 plus cosine x over x. Or you could do a table of values. And in either case, or both cases, you'll see that the function is getting closer and closer to 0 as x gets closer and closer to 0. I think now we're fairly comfortable with the concept of limit. I hope you sort of have a good feel for the definition of limit, that the limit of a function as x approaches c equals L if I can get as close to L as I want as x gets closer and closer to c. And L must be a real number, must be a fixed number. We also saw some examples of functions where they had limits that didn't exist, and sort of keep those in mind as we go along. Some functions that were poorly behaved. Next time, we're going to look at a related concept called continuity. Imagine a function that goes along without any brakes or anything. It's just a solid curve that motors along. that would be a continuous function, versus, say, that diving board function that was broken. And those are functions that are going to be discontinuous or not continuous. And we'll use this concept of continuity to be able to find roots and zeros of equations. So, thank you very much for our first lesson on limits, and I'll see you next time.